So now I'm starting. In previous lecture, I told you the continuity and some examples on the continuity. So let us do some more examples on the continuity of different type. Example 1. Let f be a function defined on R such that. Suppose you have a function which is defined like that fx. It says 0 if x is rational and x if x is irrational. Question is check the continuity in R at all point of R. So first I give you if you have this type of function, you write like that 0 to x, whatever point is given. So find the value of x. Suppose it is 0, it is coming 1 or half, whatever. So this type of function is continuous only at those points. It means in this case x is equal to 0. Otherwise, these are discontinuous. If it is coming, suppose that 0 to x minus 1. So x is equal, the function is continuous at x is equal to half and it is discontinuous at all other points. So quickly you can get the answer. But how to check? So first, continuity at x is equal to 0. Okay. So first we check the continuity at x is equal to 0. So let xn be a sequence of real number in R, because we studying in real sequence converges to 0. So you have to prove that fxn converges to f0 if it is continuous. So for epsilon is greater than 0, you can write there exists a natural number m n such that mod xn minus 0 is less than epsilon for all n is greater than m. Or you can write mod xn is less than epsilon for all n is greater than m. By definition of convergence of a single. Now you need to prove fxn converges to f0. So let us check fxn minus f0. So f0, 0 is a rational number. If x is a rational number, so this value of the function is 0. So you can write this is fxn. Here xn may be rational or irrational. If it is rational, so it will be 0. If it is irrational, so it is xn. So you can write this value will be mod xn. Whatever be the xn, it may be a rational or irrational. So from 1 and 2, we have, you can write mod fxn minus f0. This will be less than, you can write epsilon for all n is greater than m from 1. So here immediately you can write fxn, you have a sequence, this converges to 0. So you have a sequence, this converges to 0. So fxn also converges to 0. So you can write f is continuous at x is equal to 0. Now, second I am doing at x is not equal to 0 and x is rational. At x is equal to 0 I have done. Third I will check at when x is not equal to 0 and x is irrational. In this way I check the continuity at in R. So what I say, choose a sequence action. Suppose action be a sequence of irrational numbers such that this action converges to x naught. You can write this is x naught. You choose a sequence action which converges to x naught and action is irrational. So now you need to prove that f action, you need to check f action converges to fx0 or not. So here fxn. What is f action? Action is irrational. If you see the function action is irrational, so it will be x. So this will be your action. Here action, it is given that this converges to x naught, but x naught is 0. What is f x naught? X naught is not equal to 0, x is rational. If x is rational, the value of the function is 0. So fx naught is equal to 0 and fxn converges to x naught which is not equal to 0. So this cannot be equal. X naught is non-zero. So you can write fxn in this way. You can write does not converge fx naught. So f is not continuous at x naught is not equal to 0 and x naught, you can write this is x naught is rational. Now third case, when at x naught
सर
is
एक बार
not,
ये वापस बता दीजिए सर.
yes, I will tell you. First I complete this, then I will tell you. Hopefully you may understand with third condition. Otherwise no, I will tell you. X naught is rational.
सर इरेशनल होगा ना, रैशनल तो ले लिया.
हाँ, yes, you are right. This is irrational. So now again, let action be a sequence. Here I choose irrational. So here choose a sequence action of rational numbers such that action converges to x naught. If it is continuous, so whenever a sequence action converges to x naught, f action must converge to f x naught. So let us see f action. F action will be, action is a rational, so it will be 0. You can write 0 is equal to 0 into action. So action converges to x naught, so 0 into action converges to 0. But what is f x naught? fx naught is a
X
x
naught.
naught is irrational. So this is x naught which is not equal to 0. So this is cannot be value. So you can write fx and cannot converge to fx naught. So f is not continuous at x naught is not equal to 0 and x naught is irrational. Now, if anybody has doubt, I can tell you at x number in second case. Is it clear who was asking the question? Just
Excuse me, sir. Now,
Raghav,
yes, sir. Please explain the first case.
first or second?
सर
सर
सेकंड
पूरा
केस
एक
First,
सेकंड केस
first.
Second case.
यस सर
What I am saying, if x naught is not equal to 0 and x naught is equal to 0, I have done. So there may be two case x naught is rational or irrational. So what I do, I consider a sequence of irrational number which converges to x naught. So if it is continuous, so fxn converges to fx naught. Let us check. Fxn. Here xn is a irrational. So if x is a rational, so fx is equal to x. So fxn will be xn. So this will converge to x naught. Xn converges to x naught, which is non-zero. But let us check what is the value of fx naught. X naught is rational. If x naught is rational, so fx naught is 0. So here fxn converges to a non-zero number. So how it can converge to a zero number? That means fxn can never converge to a fx naught because fx naught is 0 and fxn converges to a non-zero number. So f is not continuous at x naught is not equal to 0 and x naught is a rational number. Clear?
सर
सही
वो एक्सेल हमने एक्सेल माना है कि वो इरेशनल नंबर है
हाँ.
इसमें और वो ऊपर लिखा है हेडिंग कि एक्स हम नॉन जीरो मान रहे हैं और एक्स जो है वो रेशनल है इसलिए हमने एक्स नॉट को रेशनल ले लिया है फिर
हाँ.
अच्छा ठीक है
Now you may ask a question. सर ये रैशनल इरेशनल सीक्वेंस क्यों ली? इरेशनल नंबर की सीक्वेंस क्यों ली? It exists or not? Yes. You can find in this way. For each n, you have this type of sequence. For each n, and epsilon is equal to 1 upon n, there exists this type of sequence. So this sequence xn converges to x naught. So you can write x naught minus 1 upon n, xn less than x naught plus 1 upon n. So you take n is equal to 1, 2, 3. You will get x1, x2, x3. Or between any two number, here x naught minus 1 upon n and x naught plus 1 upon n, they are infinite irrational. So एक number you can choose. So always you get an irrational sequence. Clear point?
Sir, please scroll a bit up.
Is it clear or not? You will always get that type of sequence which converges to x naught from here.
Sir,
One number, if you take n is equal to 1, तो एक नंबर इसमें से you can choose x1, you can choose any one. Another x2, x naught minus 1 y you can choose. So in this way you can get the sequence. Or we know between any two real number you will always get a irrational number. Actually they are infinite. So this type of sequence will exist. Yes. Here.
सही
In
है
this I choose rational. Like the same, this type of sequence will exist definitely for n, as I told you above. So xn converges to x naught, so fxn. Here xn is rational. If it is a rational, this is 0. So you can write 0 is equal to 0 into xn. If xn converges to x naught, so 0 into xn converges to 0 into x naught, 0. So here this will converge to 0, but so it means fxn converges to 0, but fx value of fx naught is non-zero. So fxn cannot converge to a non-zero number. So fxn cannot converge fx naught. So f is not continuous. So f is not continuous at any, f is continuous only at 0, not at any other point in R. Is it clear?
सर वो शॉर्टकट एक बार बता दीजिए आप, वो ऊपर सबसे स्टार्टिंग में क्लास में क्या बताया सर, वो 2x माइनस 1 करके कुछ सर, वो
2x
सर वो सबसे पहले क्या आपने बताया था कि सर डायरेक्ट ऐसे देख सकते हैं, वो 2x माइनस 1 आप कुछ बता रहे थे।
अच्छा, okay. What I was saying, if you want to write direct answer of this, तो होता क्या है, अगर ये सपोज करो इस तरह सीक्वेंस लिखी हुई, x is rational और 2x माइनस 1 इज इरेशनल, तो वाट एवर विद द वैल्यू आप इसको इक्वल रख दीजिए, तो वैल्यू फाइंड आउट द वैल्यू, तो दिस इज 1, तो x इक्वल टू 1 पे कंटिन्यूअस होगा और अदर पॉइंट पे ये डिसकंटिन्यूअस होगा. यू कैन गो यू कैन नो द आंसर डायरेक्टली.
ओके
Okay,
सर,
here 0 is equal to x, so x is equal to 0. That means it will be continuous at x is equal to 0 and discontinuous at all other point. Clear point?
क्लियर सर। और सर अगर क्वाड्रेटिक कोई दो रूट आ गए तो फिर
Now, whatever be the equation, put and find the root of x.
ओके सर, थैंक यू सर।
It may be like that 0 and x square minus 1. So x square minus 1 0, so x is equal to plus minus 1. So at 2 point this will be continuous, at all other point it will be discontinuous. Clear?
क्लियर सर।
So now, so I have done this thing. Now let us do one more example. This is a nice example. It says, suppose you have a function from R to R, satisfy this condition, fx plus y is equal to fx plus fy. Okay, for all x and y element of R. If it says if f is continuous, if f is continuous at 0, then f is continuous at every point x naught in R. If a function satisfies this condition and it is continuous, then it is continuous at every point. Let x naught be any point, arbitrary point. Okay, now what is f0? So here I am deriving some condition from the given condition. You can write f0 plus 0. This is f0. So from here you can write f0 is equal to 0. Now you can write f0 is equal to fx minus x. By above condition you can write fx plus f minus x. f0 is equal to 0. So this is fx plus f minus x. Or this is f minus x is equal to minus f. I am driving. These results are true if a given condition is true. That is fx plus y is equal to fx plus fy. Now, one more thing. f0, sorry. Now, what is fx minus y? So, fx minus y, you can write fx plus f minus y. Okay. And this is fx, f minus y, you can write f minus y, fx minus y. So this is another condition you can write. Fx minus y, you can write fx minus y. Now, let xn be a sequence converges to x naught. It means xn converges to x naught. So I am writing in a compact form. You can write xn minus x naught. This will also converge to 0. This is the simple. Now, you can write, you need to check fxn minus fx naught. This you can write fxn minus x naught. So here, since xn minus x naught converges to 0 and f is continuous, so can I say this will converge to f0? Since f continuous at 0. So an xn minus so you can write this is f xn minus f x naught. This is converging to f0. f0 is equal to 0. So here you can write f xn converges to f x naught. So here f is continuous at x naught and x naught is arbitrary. So f is continuous at x naught for all r. So this is an example. You can say if it is continuous at 0, then this will be a continuous at each point in R. Now I am doing a nice property of continuous function. You know this property. On closed interval. What it says, I am telling first I give the definition. What is bounded? Suppose you have a subset, S is the subset of R, and f is a function from S to R. F, this function is called bounded on S if its range is bounded. If its range, if the set, you can write set f as, you can denote this is fx, x is the element of S, is bounded. So if you have S is the subset of R and f is called, function is called bounded if its range is bounded. Now there is a nice result. It says if a function f is continuous, is continuous on close interval, that is important, close interval, then it is bounded on AB. So you can say every continuous function is every continuous function on a closed interval is bounded. Suppose you have a function fx is equal to x square. Interval is you are taking 10 to 100. So fx is continuous, closed, and this is bounded. So f is bounded. But it is not true if you cannot say if interval is open. For example, if you take the interval this 0 to infinity. So here this is not, f is not bounded. I can give you one more example. If you take fx is equal to 1 by x, this is continuous and interval is this you take. So this is not bounded. F is not bounded because it is continuous, but you are taking open interval, semi-open, it means this is not bounded. So it means if f is continuous and interval is not closed, then you cannot say it is closed. It is f is bounded. However, it may be a chance that if you take, in this case, if you take interval, open interval 10 to 100, then this is in this case f is also bounded. So what I am saying, if f is continuous and interval is closed, then you can say 100% f is bounded. But if interval is open, so it may or may not. It may be a bounded, it may not be a bounded. It depends upon the function. You can see if 10 to 100 in open interval, it is still bounded. But here as f is equal to x square, you are taking semi-open 0 to infinity, not closed. It is not bounded. Even it is continuous. Third example, if f is equal to 1 upon x, this is also continuous in open interval 0, 1, semi-open interval, but it is not bounded. So may or may not. So up to here, if anybody has doubt, tell me. Otherwise, I tell you a interesting property IDP.
सर बाउंडेड एक बार फिर से बता दो कि
बाउंडेड में उसका सेट जो है वो बाउंडेड होगा, और बाउंडेड की डेफिनेशन मैंने लेक्चर 1 में बताई थी. जो इसकी रेंज है ना, ये सेट बाउंडेड क्या होता है? ये सेट इज बाउंडेड अगर देयर एग्जिस्ट ए रियल नंबर k1, सारे एलिमेंट लेस देन k1 हो और ये k2 हो. बाउंडेड अबव, बाउंडेड बिलो.
सर एक बार ऊपर के डेफिनेशन वापस से दिखा दीजिए ना.
बाउंडेड मीन्स इट्स, ये जो सेट है ये बाउंडेड अबव हो एंड बाउंडेड बिलो. दिस इज सेट. is when a set is said to be bounded if it is bounded below as well as bounded below above. Okay.
Yes,
Okay.
sir.
Aditya?
Yes, sir. Yes.
Now I am doing in that is intermediate value property. This is known as in short IVP. What it says, let f be a continuous on closed interval AB and let FA is less than S is less than FB. That is what here? S is a intermediate value. S is a value which is intermediate between two values taken by f. So suppose f is continuous on AB and S is any value between FA and FB. It says then there exists a point x naught such that how A is less than x naught B, a point between A and B, and f x naught will be S. So this is IVP. If f is continuous and there is a point f s between A and B, so there exists a point in between A and B such that the value of the function at that point is S. Geometrically, I can show you what it's saying. Suppose you have a function like that. F, this point is A, at this point is B, or this is FA, FB. You can take in negative also, there is no problem. If anybody has. A. Okay, so what say? Suppose you have a point here S1. S1, a point, the corresponding there will be a point X1 where Fx1 will be S1. If there is suppose here S2, this is the value S2. So here will be a necessary a point X2 where Fx2 will be S. Same thing, if here is S3, yeah, any other point, so here will be X3 which lie between A and B such that Fx3 is equal to S. So this is the IVP. If anybody has doubt, ask me about IVP.
Sir, please explain again this geometrical part.
Yes?
Sir, please explain this geometrical part again.
What I am saying, suppose f is a continuous function, this is a continuous function, and A is this and B is this. So what it says, if it is continuous, it takes all intermediate value. It means if you take this value, suppose this is S1. So there must exist a point X1 corresponding to S1 such that the value of function at X1 will be S1, that Fx is better. If S2 you take here, so there must exist a point X2 between A to B such that Fx2 is equal to S. If you take X3, तो Fx3 कहीं भी आप ले लीजिए point, you will always get a point on x-axis, yeah, between A to B such that the value of the function at that point will be equal to the S. Like that. Anywhere. Clear point? Who was asking the question? Clear or not?
Yes, sir, clear.
No. Any other doubt? No. Let us do one or two example. Question is, so that equation, suppose you have 1 minus x cos x is equal to sin x, has at least one root, a solution. Yeah, you can write solution in open interval 0 1 solution. So if this type of equation is given, you consider a function let fx 1 minus x cos x minus sin x. So now I will apply the IVP, because IVP say if I how I apply the IVP, let us see. First is, if you apply the want to apply, so you need to check this is continuous between 0 to clearly f is continuous in 0 1, 0 1. Okay, because cos x is continuous, sin x is continuous, 1 minus x is continuous, product of two function is continuous, and subtraction of two continuous function is continuous. Now let us see what is coming between f0. f0 is right, I think it is 0 0 1, I think 1, which is positive. Now you can take f1 by 2 also, yeah, f1 by 3, yeah, you can take f1 by 4, but you will get some good thing from which you can conclude some significant thing. That is, if you take f1, so f1 will be minus sine 1, which is less than 0. If you take suppose f1 by 2, so 1 by 2 cos 1 by 2 minus sine 1 by 2. So it is very typical that ये function 1 by 2 पे positive है, negative है. This is little bit tricky. You can check, but this is little bit tricky. But here, if you take f1, so easily you can check this is negative or positive. Clear point? Why I am taking this? So you have no need to take this type. So here f0 1, f minus 1, this is positive and 0. So it means since 0 f1 is less than this f0, f0 is positive, f1 is negative, 0 will lie between this point. Since here write f1. So by IVP, it is continuous between 0 to 1 and 0 lie. So there exists x naught between 0 to 1 such that f x naught must be 0. f x naught, here s is equal to 0. So what is the equation? 1 minus x naught cos x naught minus sin x naught is equal to 0. 0 is less than x naught 1, or you can write 1 minus x cos x naught, this is sin x naught. It means x naught is the solution of this equation. 1 minus x cos x sin x. So you can say, so x naught which line is a solution of equation 1 minus x cos x is equal to sin x. यही आपको प्रूफ करना है. Has at least one root, one means one solution. We are definitely true that it has at least one root. It may have 2, 3, 4, I don't know. But from IVP, I have confirmed that it has at least one root. Any doubt? No? Okay. Now I'm doing next nice example. Mostly you use this result so that a polynomial of odd degree, a polynomial of odd degree has at least one real root. You know this result. So let us prove by using IVP. Let fx, this is an xn plus an minus 1 xn minus 1 plus a1x plus a0, and an is not equal to 0, and be odd, be a odd degree polynomial. You consider fx an x to the power n. If an is not equal to 0 and n is odd, be a odd degree polynomial. This is a odd degree polynomial. Okay. Now you need to prove that it has a root. So an is not equal to 0. So I am taking x raised to power n common. So you can write like that: an plus an minus 1 x raised to power n minus 1. Sorry, this is not x to the power n. So this will be x a n minus 2. This will be x square plus a1 over x n minus 1 plus a naught by x. Suppose this is 1. So here an is not equal to 0. So an can be positive or negative. Clear point or not? N may be positive or negative. So you need to
Yes.
prove for both cases. If an is greater than 0, if this is positive, so what can you say? Fx. Can I say an is positive if x tends to plus infinity? Yeah, so what will fx will approach plus infinity, n is odd, so plus infinity, it will be a plus infinity. And fx will approach if x is approaching minus infinity, because you are working on r, minus infinity to infinity. So x minus infinity, an is positive, all these terms will be 0. X is equal to minus infinity, power odd, so it will be minus infinity. And f is continuous. Why it continuous? Because this is a polynomial. So by and minus infinity is less than 0 infinity. 0 will lie. So by IVP, there exists X naught in R, or if some student have confusion, you can write minus infinity, X naught is infinity, such that f x naught is equal to 0. So in this case, every odd degree polynomial has one तो होगा, more than one I don't know, तो you can write has at least one real root. So if an is greater than 0, this is over. Now case second. If an is less than 0, it may be a chance. So what will be fx? If x is plus infinity approaching, so an is negative x infinity, all these terms will be 0. So n negative, infinity negative, positive, so this will approach to minus infinity. Sign will be. If fx will approach, if x approaching minus infinity, so here x की power n is odd, तो minus infinity, an is negative, so this will be positive. All other will be 0, so this will approach to infinity. Same thing, f is continuous. On R and minus infinity, 0 is less than infinity. So by IVP, there exists again x naught element of R such that fx naught is equal to 0. So again you can say, so every odd degree polynomial has at least one real root. So if anybody has doubt, ask me. So you can see, normally you use this result again and again. The proof is here. IVP with continuity. Any doubt? Today you are not asking any doubt.
Clear, sir.
No doubt, sir.
Clear, sir.
No doubt. Okay, now I am stopping my lecture. Now stopping lecture.